Hi there everyone, and welcome to this video on differentiating more complex functions. Now, the only reason this is more complex is just because the functions themselves aren't ready to be differentiated, and we know that because we can only differentiate functions if they're in the form ax to the n. What I mean by that is, take this one for example. That is easy to differentiate. Times by the power, reduce the power by 1. And the a is 3 and the n is 4 and the x is just the base value. This is the same. We just don't bother writing a 1 there, for example, but the a would still be 1, and we can differentiate these easily. Even a more complex one, something like this, we can still do that. We have to think a bit more, but it's still written in the form ax to the n, a coefficient in front of a base value, and that base value is raised to a power. Check, check, check. This one, however, is not that case. So, I didn't want the y there. So what we've got to think about is our indice knowledge, and is it any good basically? And if it isn't any good, if you don't understand why this works, then I'm not going to explain it in this video. I'm just going to do a shortcut around the patterns. When your indices get better, it will pull this up to where it needs to be, but it's not the end of the world at this point. So what I want you to be able to realize is when you look at that, this is the same as 3 times 1 over x. That would give me exactly the same answer. Now 1 over x is actually the same as x to the minus 1. Now, like I just said, I'm not going to explain necessarily why that works, but what's actually happening, if I flip this over, I get that, or just x. And there's a power of 1 there, but when I flip it over, so there's no fraction anymore, that becomes a minus 1. So basically, if it's 1 over x, the x is now on the top, and the power is going to change to a negative. So this is now in the form ax to the n. Let's have a look at a few more. After you've seen 3 or 4, you'll get the idea. So this is the same as 5 times 1 over x. 1 over x is the same as x to the minus 1. That power is now just become negative, which is the same as 5x to the minus 1. It is in the form ax to the n. Let's have a look at another. Okay, so we've got the squared now, so just got to be careful, but it's exactly the same. It's 4 times 1 over x squared. So it's got 4 times. Right, what do you think is going to happen now? The base is still x, it's still going to be a 2, and it's still going to be a minus. Okay, it was a 1 before, now it's a 2, nothing changes. So it is now in the form ax to the n. So by now, maybe it's getting a little bit better for you. This is the same as 7 times 1 over x squared. That is the same as 7 times x to the minus 2. That is the same as 7x to the minus 2. Same pattern, repeated. This one's a bit trickier because you've got the 3/5, but actually, check this out. That is 3 over 5 times 1 over x cubed. You know, when there was a 4 there, like this one for example, there's also a 1 there, so I just don't write it because we don't need to. So there's always a number there. It's just when you see it, you're not used to seeing it, you don't think about the problem enough, and you make it complicated, but it's not really. So power is positive, so let's bring it to the top. The power is now negative. So it's 3 over 5 x minus 3. It is now in the form ax to the n. Okay, so now let's start differentiating these terms. So I'm going to skip that whole stage now, and you can too. This is all you would be expected to write. So you rewrite y in the form ax to the n. Then we're going to differentiate. So dy by dx times by the power and reduce the power by 1. Now, I just want to point out that this is as far as you would need to go, but you'll see later, if you can go to this stage, it is much better for you. Now this is the same as that. Well, if you undo that process from what we were doing before, it's the same as 1 over x squared. The power is now positive, which is now the same as that. So I would really encourage you to go to this level, but these are the same, and for GCSE this is a fine answer. Okay, let's have a look at this one. So this is the same as 2x to the minus 2, just for the same reasons. I just don't want to keep repeating myself. So if you need to write a few more steps down, that's fine, or you just want to look at the patterns, that's fine also. Let's differentiate. Times by the power, reduce the power by 1. This is the same as minus 4 times 1 over x, sorry, getting ahead of myself, x to the minus 3. Well, that is the same as 1 over x cubed. So to put x on the denominator, the power is now positive. That's a shortcut. It's not maths, this is just a shortcut. So this is the same answer. Okay? That's a better answer, but this is absolutely fine here. Okay, so two terms. So we're used to doing 2 or 3 term equations, just not with these complex ones. But this is the same as 3x to the minus 1. Minus 4x squared. Always really important. Don't start differentiating one term and rewriting another. It's just going to go horribly wrong. So just copy that one down. Differentiate. Minus 3x to the minus 2 minus 8x. Or maybe you can see the patterns now. It's going to be minus 3 over x squared minus 8x. Right, so let's step it up a notch. Okay, so here we have a function. I've just rubbed out that bit there. So y is equal to 4 over x plus 3x. Now you probably don't know what this function looks like. It's a reciprocal, if that means anything to you. But we're going to have a look at it in a minute. So find the gradient of this function when x is 2. Well, to find the gradient, we need the gradient function. So we need dy by dx. We can't differentiate this because this term is being a bit of a nuisance and we need to rewrite it in the form x to the n. So just pop it under here. So that's 4x to the minus 1 plus 3x. Now we can differentiate and we'd have minus 4x to the minus 2 plus 3. Or minus 4 over x squared plus 3. You'll see now that this is much easier to use, but you have a calculator, so honestly it does not matter. So find the gradient when x is 2. So this is our gradient function, here's our x, let's sub a 2 into there. You can use your calculator to do that, but if you've done it this way, you can just do it in your head. So when x is equal to 2, dy by dx is equal to minus 4 over x squared, so that's another 4. Minus 1 plus 3 is 2. So the gradient is 2 when x is 2. That's a coincidence. Alright, find the coordinate, okay, when the gradient is minus 6. So this time, minus 6 is going to equal my gradient. Now, the problem is, with this one now, it's going to get hard. So this is a point where, this year especially, it might exceed what your knowledge is. In the 5th year, or year 11, whatever you call it, you'll catch up, you'll be much happier at this stage, but it might take you a year to get that fluency with your indices, because indices are tough. You know, I've done it 1,000 times, so it's easy for me, but I remember how tough it was. So a gradient function is now set to 6. So this is a negative term, so I'm not happy about that. So I'm going to make that positive by bringing it onto the other side, which means I need to get rid of this as well. So for times by x squared divided by 9, or pull the switcheroo, whatever you want to call it, you get this. And if I, some just random writing there. So if I square root both sides, I get plus or minus 2/3. Don't forget the plus and the minus. Well, actually, this is the x coordinate. So what we have is we have minus 2/3 and we have 2/3. So this is happening at 2 places, and I'll show you why it's happening at 2 places in a minute. And we need the y value. So look, here's our coordinate, our formula for the y values. So I'm going to type in minus 2/3 on my calculator, and I'm going to sub that into here. So I'm going to do 4 divided by my answer plus 3 lots of my answer, and I get minus 8. I'm going to do exactly the same thing, but with 2/3. So 4 divided by my answer plus 3 lots of my answer, and I get 8. Okay, so there you have it. So let's have a look at this graph. I've got it already made. I think I've already got it open, in fact. Here it is. So let's just get these off. So that is actually what the graph looks like. It's a funky looking reciprocal. If you put a point on, draw a tangent, calculate the gradient of that tangent. Let's bring it up here. So we were just working out 2/3. So if I try and get that point as close to 2/3 as I can, that's 0.69. You can see the gradient is minus 6. And you can just over here see that the y value is pretty much 8, so we know we're right. And that also happened down here as well. Oh, it's going the wrong way. So that is why, there you go, there were 2 values where the gradient was minus 6, because there are. Yeah, it's just down to the nature of the graph. And what else did we try and find when the gradient was 6, wasn't it? So if I keep moving this up, it's going to go steep pretty quickly. I'm just going to have a look at the value on the right. You can't quite see it, it's out of slot. Oh, it doesn't matter. But it, I can probably do it. Here we go. Oh, I've got to go miles. What's my answer? Oh, I was minus 6. Come on, Greg. It's pretty much a straight line, that one, isn't it? So you can see it's really not changing. So minus 6. Let's move this back down. Oh, let's see, it goes up really fast. Okay, roughly about there. So that coordinate is 0.7, and our answer was 2/3. I've just done the same question twice. What an idiot. Right, sorry about that, guys. Right, last thing I'm going to talk to you about is differentiating this. Now, to do this, let's consider a really easy fraction problem, so like, year 4s could do. Right, to do that, you go, oh, I'm all over this. That's 5/7, wouldn't you? That's great, because we've got the denominators the same, and we've got like terms, we've got number terms. But here we've got, they're not like terms, so we can't just collect these together. But what we could say about this one on the right is this is the same, right? That is what we did. So what we're going to do is go from here to here. You can see the 1 is actually being divided by 7, and so is the 4. We're going to split the denominators. So if we do that, we get x squared divided by x plus 3 divided by x. We've split the denominators. Well, anything squared divided by itself is just an x, so like 3 squared divided by 3 is just 3, for example. And this is x to the minus 1. This is now in the form x to the n. We can differentiate, so dy by dx would be equal to 1 minus 3 x to the minus 2, or for those diligent pupils out there, it's 1 minus 3 over x squared. Guys, a lot of information. I appreciate this is going to be a really hard lesson for you, so take your time with it, and I hope it all makes sense.